am Mr. P. Mabuhussain, Assistant Professor of EEE in Institute of Aeronautical Engineering at Hyderabad. So today in this video we are going to discuss about numerical problems on inductance of single phase line. So let us see the first problem. So the problem is a single phase transmission line has two parallel conductors, so 3 meters apart. Here we are having two parallel conductors, so which are 3 meters apart. The distance between the two conductors will be 3 meters, and the radius of each conductor being 1 centimeter. So radius of each conductor will be given as R is equal to 1 centimeter. It is for both the conductors, so R will be the same, so 1 centimeters. So now you have to calculate the loop inductance or total inductance, so per kilometer length of the line. So here you have to calculate the loop inductance per 1 kilometer length of the line. So if the material of the conductor is copper, and the second time it is steel with a permeability of 100. As you know, so the relative permeability of copper is equal to 1, and steel permeability is given here, which is 100. Mu r is 100. So now you have to do the this calculation of inductance for this transmission line. In the both the case, if the conductor is copper, so what will be the total inductance? If the conductor is steel, what will be the total inductance? Okay. So here to calculate the inductance of any conductor, so if it is the conductor 1 and if it is the conductor 2, now the inductance for calculating the conductor 1, so will be given by the equation mu by 2 pi into ln d by r1 dash. So to calculate the inductance of conductor 2, equation is L2 is equal to mu by 2 pi ln d by r2 dash. Here mu is nothing but mu naught into mu r. Okay, so when you are considering the first case, so in which a conductor is copper, so that mu r value you have to consider it to be equal to 1. So in the second case, in the conductor is steel, so then you have to consider the mu r value as equal to 100. Now the mu naught value you already know, this value is 4 pi into 10 power minus 7. Okay, and the distance between the conductor, capital D value is given here, so which is equal to 3 meters. Okay, distance between the two conductors, it is given as 3 meters, right? When you convert this meters into centimeters, then you have to multiply with 100 or 10 square, so that it will be given in centimeters. So the D will be 300 centimeters. Okay, so now R dash, so this R dash is nothing but 0.7788 times the radius of your conductor. Okay, radius of your conductor is given as 1 centimeter. So R dash value you can calculate by using this expression. R dash is equal to 0.7788 times R. So if you substitute R is equal to 1, you will get 0.7788 will be the value of R dash. Now that loop inductance, so loop inductance or total inductance of this single phase transmission line will be equal to sum of the two inductances. So inductance of conductor 1 and inductance of conductor 2. So if you sum both the two, you will get the value of total inductance of the line. Okay, so now as you know, from these two equations, L1 is mu by 2 pi into ln d by r1 dash, and L2 is mu by 2 pi into ln d by r2 dash, right? So now here if you substitute in this equation, so which is the total inductance or loop inductance, so then you will get the L is equal to mu by 2 pi ln d square by r1 dash into r2 dash. Okay, so now here if you take square and under root, now this total square, it will be bring back to front side. So the inductance, total inductance equation will be L is equal to mu by pi into ln d by r1 under square root r1 dash r2 dash you can take. Okay, so here r1 dash is the 0.7788 times the r1, and r2 dash is the 0.7788 times r2, right? In the both the case, r will be the same, which is 1 centimeter. So r1 and r2, r1 dash and r2 dash, so both will be the same, which is equal to 0.7788 centimeters. Okay, so by taking these values, you have to calculate the inductance, so total inductance of the single phase transmission line in both cases. So in one case, the conductor material is copper, so the mu r value will be equal to 1, and in the second case, the conductor material is steel, and the relative permeability will be given as 100 here. Okay. So first take the first case here. Okay, as you know, the distance between the conductors, capital D value here will be 300 centimeters. So in the given problem, distance D is given in meters, 3 meters. We are going to convert that value into centimeters. So you have to multiply with 10 square. So you will get 300 centimeters. Okay, that is the value of your capital D. And radius of each conductor is given here. Okay, so radius of each conductor R1 and R2 both will be the same, which is equal to 1 centimeter. Okay, so now we are taking the first case in which the conductor material is made up of copper. So for copper, the relative permeability will be equal to 1. So that means mu r is equal to 1. So the loop inductance equation L will be according to this equation. So L will be equal to mu by pi into ln d by under square root r1 dash into r2 dash. That equation you have to take here. So L is equal to mu by pi into ln d by under square root r1 dash r2 dash here. Okay. So as you know, r1 dash and r2 dash both are equal to 0.7788 times r. So and r value is equal to 1 centimeter. So this value will be 0.7788 centimeters you will get. Okay. So both r1 dash and r2 dash, both the value will be 0.7788 and d is 300 centimeters. Okay. So now in place of mu, you can substitute mu naught into mu r by pi ln. So d by under square root. As r1 dash and r2 dash both are the same, you can take r1 dash and r2 dash will be equal to r dash, so that it will become r dash whole square. So this square and this square will get cancelled. So you will get mu 0 mu r by pi into ln d by r dash only. So now if you substitute the values here, mu naught value is 4 pi into, so 10 to the power of minus 7, and mu r value for copper is 1 by pi into ln. So d is 300 centimeters and r dash is 0.778. Okay. So now here pi and pi will get cancelled. So the value will be 4 into 10 power minus 7 into ln 300 by 0.7788. Okay. So now if you calculate this value, so by using your calculator, so you will get the value of total loop inductance, which is L equal to 23.8 into 10 to the power of minus 7 henries. Okay. So this henries is per meter only. Okay. So by using this equation, you will get the value of inductance in henries for 1 meter. So henries per meter only. But if you go to the problem, so here you have to calculate the loop inductance per kilometer, not for 1 meter. So once you know the value of inductance for 1 meter, so then for kilometer in the sense 1000 meters you have to calculate. So the loop inductance per kilometer will be equal to, so the inductance value per meter into total number of meters in 1 kilometer, so which is 1000. So if you multiply this value with 1000, you will get the inductance value per kilometer. Okay, that value you are getting finally it would be 2.38 into 10 to the power of minus 3 henries, and 10 power minus 3 you can call it as milli. So 2.38 milli henries you will get. Okay, so this is how you can determine the loop inductance if the conductor material is copper. So as copper, you know, the relative permittivity would be 1. So now in the second case, you have to consider the conductors are to be steel conductors. And the relative permeability of steel, it is already given in the problem. So that value is 100. So mu r is 100 here. Okay. So now here you have to take the same equation again. So this value. Okay. So from this, L is equal to mu naught mu r by pi into ln d by r dash. Same equation you have to take. Okay. So then, so mu naught value you already know. So so again I will write. So I will erase it first. Okay. So L value is equal to, so mu naught mu r by pi ln d by r dash. So this is the loop inductance or total inductance of single phase transmission line when the radius of both the conductors are same. Okay. So now the R dash value already we were calculated, which is 0.7788 times R, and R is 1 centimeter. So this value is 0.7788 centimeters. And capital D value already given, it will be 3 meters, which is nothing but 300 centimeters. So the value of inductance, so when you consider the steel conductors, mu R value is 100. So L is equal to 4 pi into 10 power minus 7. So it is the value of mu naught. So multiplied by, so mu R is 100 by pi into ln. So D is 300 and R dash is 0.7788. Again here pi will get cancelled. So this value is 4 into 10 power minus 7 into 100 ln 300 by 0.7788. Okay, so this is the total inductance or loop inductance per kilometer, right? This is the henries per meter, this value. So this is the henries per 1 meter. Now you have to get the value in kilometers, you have to multiply this total value with 1000. Okay, so now if you calculate the loop inductance per 1 meter, you will get 122.8 into 10 to the power of minus 7. Now if you calculate for 1 kilometer, you have to multiply this value with 1000, so that you will get the loop inductance per kilometer will be equal to 12.28 millihenries. Okay, so this is how you can determine the inductance of a single phase line. So if two conductors having the same radius, and suppose if the conductors are made up of different materials, so first with the copper and second with the steel, how you can determine the inductance we have seen here, right? So let us see another problem. So here in a single phase line, conductors A and A dash in parallel form one circuit. So while conductors B and B dash in parallel will form a return path. Okay, so calculate the total inductance of the line per kilometer, assuming that current is equally shared by the two parallel conductors. Conductor diameter is given as 2 centimeters. Okay, so here you see here it is a single phase line. As you know, single phase line will be having generally two conductors or two phases. So here in one conductor or one phase will be acting as forward path. So that means current will flow in forward direction. So another conductor will act as a return path, which is current will be in the reverse direction. Okay, so but here in the problem they are saying that so each conductor, so one circuit will be having two conductors. That means phase A, if you take one circuit, and phase B, if you take another circuit, then this is having two subconductors and this is also having two subconductors, right? For phase A, subconductors are A dash, they are given, and for B conductor, so the subconductors are B and B dash. Okay, so now here the distance between these A dash and B, so this is given as 100 centimeters, and between A and A dash it is given as 20 centimeters, and BB A dash also 20 centimeters. Okay, it is given on a horizontal surface, and here they are saying that the conductor diameter will be equal to 2 centimeters. That means small d value, it is 2 centimeters each conductor diameter. So once you know the diameter, so then you can calculate the radius, which is the half of the diameter. So this value will be equal to 1 centimeter. Okay, so now this problem you have to calculate using self GMD and mutual GMD method. Okay, so now the to calculate the inductance, the equation for loop inductance per kilometer will be equal to 4 into 10 power minus 7 ln dm by ds. Okay, so this is per kilometer. So generally the equation for loop inductance will be L is equal to 2 into 10 power minus 7 ln dm by ds henries per meter. So this is for one conductor only. So that means for one conductor. So second conductor also the same. So 2 into 10 power minus 7 ln dm by ds. So which is in henries per meter again. So the loop inductance will be, you can call it as total inductance. Okay, loop inductance or total inductance will be sum of two inductances. of each conductor, L1 plus L2. In such a case, if you calculate this value, you will get 4 into 10 power minus 7 ln dm by ds you will get. So this value is in henries per meter. So that means the inductance value will be in henries, and this if you calculate by using this expression, you will get only for 1 meter length of the conductor. Okay, the inductance in henries per 1 meter length only you will get from this expression. Now if you want to calculate the inductance per 1 kilometer, then you have to multiply this expression with 1000. Okay, once you multiply this expression with 1000, here 1000 in the sense 10 cubed, right? So 10 cubed. Here you are having the 10 power minus 7. Here you have the 10 cubed. So then, so you can write final equation will be equal to 4 into 10 to the power of minus 4 ln dm by ds. So which is now, it will be henries per kilometer. Okay, so this is the expression. Okay, so this expression we are going to use here. Okay, the loop inductance or the total inductance for 1 kilometer will be 4 into 10 power minus 4 ln dm by ds, henries per 1 kilometer. Okay, so now here, what is the value of dm and what is the value of ds? You have to calculate. Dm here is nothing but mutual GMD and ds is nothing but self GMD. Right. So first to calculate the dm. So dm is the mutual GMD. Now while calculating the dm value, so you have to take all the products which are the mutual distances from one phase to other phase, right? So if you here you are having, this is one phase, so this is another phase. Each phase is having 2 subconductors, right? Now you have to take all the possible mutual distances from phase A to phase B, or line A to line B, you can check. Okay, so now mutual distances here are A to B, one distance, A to B dash is another distance, right? So DA B one distance, DA B dash is another distance. Now if you take this A dash subconductor in line A, so then the mutual distances will be A to B, and so A dash to B, A dash to B dash. That means the distance from A dash to B and the distance from A dash to B dash you have to consider, and you have to take all the products whole to the power of 1 by total number of conductors in line A, so which is equal to 2, multiplied by total number of lines subconductors in line B, so which is again equal to the 2. So this is the value. So this will be DAB, DAB dash, D A dash B, D A dash B dash whole to the power of 1 by 4 you will get. So now by using this expression, you can calculate the value of dm. Okay, so 1 by 4 is nothing but 4th root of the total value. So DAB, D A B dash, D A dash B, D A dash B dash, right? So while calculating mutual GMD, you have to take all the possible mutual distances, right? You have to take the product of all the possible mutual distances and whole to the power of 1 by total number of conductors in phase A, total number of conductors in phase B. You have to take multiplication. Okay, so this is the equation, right? Now what is the value of distance from A to B? DAB is nothing but distance from A to B. Okay, so distance from A to B, so from this figure you have to write. Okay, so I will erase this. Okay, so now, so from that figure, so distance from this A to B, so A to B, this distance is DAB, so that value will be equal to 100 plus 20, so which is 120. So 120, so multiplied by, so then DAB dash, so A to B dash distance is 20 plus 100 plus 20, so this will be 140 multiplied by, so DA dash B, so this value is 100, so multiplied by DA dash B dash will be 120 whole to the power of 1 by 4. Okay, so now if you calculate this value, you will get 119 centimeter. Okay, so you are getting mutual GMD will be equal to 119 centimeters. So then once you know that mutual GMD, then you have to find out the self GMD, right? So now this self GMD you have to calculate for each line or each phase. So here in the single phase transmission line, you will be having two phases or two lines here. So one is forward line, another one is a return line, right? Each phase is having again two subconductors. Okay, so now thus for each line you can calculate the self GMD. The self GMD of line A you can call it as DSA, and self GMD of line B you can call it as DSB here. Okay, now as these two are having the same number of subconductors, and also the radius of conductors also will be the same, so then this generally these two values will be same. So why? Because so these two, phase A and phase B, are having two conductors, right? Two subconductors, and also the radius of each subconductor will be the same, which will be equal to 1 centimeter. Okay, so as the radius of conductors are same, and each phase is having the same number of conductors. At the same time, if you observe the distance between the subconductors in phase A and phase B, so again the distance also will be the same. So now in such a case, if you calculate the DSA or DSD, so you will get the values will be same. So here you can calculate only one DS, so that it will be the same as another one. Okay, so first you can calculate the DSA here. Okay, so you calculate DSA. So now here, while calculating the DSA, you have to consider only the subconductors in that line or that phase. Okay, so that means DSA you can calculate by considering this subconductor A and subconductor A dash both only. Okay, so now you have to write the all possible distances, okay, by considering the self also. Okay, now if you consider the first subconductor, how many possible distances you can take? So DAA, so if your self distance, so DAA you can take, and the distance is DAA dash. Okay, so this, let it be one set. Okay, now if you take the second subconductor A dash, then self distance DA dash one distance, and DA dash A is another distance, whole to the power of 1 by total number of conductors square you have to take. That means here in line A you are having two conductors, so 2 square you have to consider. So this value will be equal to DSA, self GMD of conductor A or line A. So this will be equal to, so DAA, DAA dash, DA dash A dash, DA dash A whole to the power of 1 by 4. Okay. So now here the value of self distances DAA as well as DA dash A dash. So this value will be equal to R dash. Okay. So R dash of value. R dash here is nothing but 0.7788 times R, and the R value is 1 centimeter. So 0.7788 will be the value of DAA or DA dash A. Okay, so here you are getting DAA, which will be equal to DA dash A dash will be 0.7788 centimeters. Now the distance from A to A dash as well as A dash to A, both will be the same. A to A dash or A dash to A, that will be equal to 20 centimeters. So you got all the values in this equation, okay, which is derived here. Okay, so 1 by 4 is nothing but fourth root of DAA, DA dash, DA dash A dash, DA dash A. So now here you got all the values, all the distances, all the 4 distances. Simply you need to substitute in this equation. So DAA is 0.7788 and DA dash is, so this A dash is 0.7788. Again DA dash is 20 and DA dash is again 20. So now if you take the fourth root of all these products, so then you are getting 3.94 centimeters. Okay. So now you got the self GMD as well as mutual GMD, right? DSA, and this is mutual GMD DM. Okay. So now according to the first equation, L is equal to 4 into 10 power minus 4 ln dm by ds, which is in henries per kilometer. You can calculate the total loop inductance per kilometer. So right, so you substitute the dm and ds, so these two in this equation, so that you will get the total loop inductance for this transmission line system. So the value of L will be equal to 4 into 10 power minus 4 into ln 119 is the dm value, and ds value is 3.94. Okay, now if you calculate this value, then you will get the value in henries per kilometer. So which is 1.36 into 10 power minus 3 henries per kilometer. And this minus is, you can write it as millihenries. Okay, 1.36 millihenries per kilometer you are getting. Okay, so this is how you can determine the inductance of a single phase line. So if the line is having two conductors in each line. Okay, so two subconductors. Like, right, another problem. So here the same single phase line you are considering. So the arrangement of conductors of a single phase transmission line is shown in figure. Okay, now wherein the forward circuit is composed of three solid wires of 2.5 mm in radius. So return circuit is composed of two wires of radius 5 mm placed symmetrically with respect to the forward circuit. So find the inductance of each side of the line and that of the complete line. Okay, here also a single phase line is given. So but in this single phase line, if you observe, so one phase, so which is called a forward circuit, it is having three wires. Okay, three subconductors are there, and another phase or another side, so which is the return circuit, that is having only two conductors. In the previous problem, in the second problem, so both the phases are having the same number of conductors. Okay, two conductors and two conductors. But here, different number of conductors, different subconductors are there in the each phase. So in one phase you are having the three subconductors. In another phase you are having the two subconductors. Also, the radius of wires or subconductors also different in both the circuits. Right? Here in this side A, the radius will be 2.5 mm here. Right? So that means you have to represent this as a R1, as or if you or you can even take it as RA here. So radius of each subconductor in side A is RA is equal to 2.5 mm, and in side B the value is 5 mm. So side B radius is RB, so which is 5 mm. Okay, and also in the figure here, so the distance between these two lines is given as 8 meters. So which is the capital D, you can say. Okay, so then the distance between subconductors 1 and 2, it is 4 meters, and 2 and 3 it is 4 meters, and 4 and 5 it is 4 meters. And they are saying another point is that, so the conductors are symmetrically placed with respect to the forward circuit. Okay, so in the return circuit, the conductors are symmetrically placed with respect to forward circuit. So as it is the forward circuit, right, symmetrical, the two conductors in the return circuit are placing in symmetrical manner. So that means if your conductors are like this, in the middle you are having the conductor. Right? So as you are having here, in the middle you are having another conductor. Okay, so that means the distance from here to here and distance from here to here will be the same. Similarly, distance from here to here and distance from here to here will be the same. So that distance is given here. So 2 meters. Okay, so from here to here, the distance is given 2 meters. The similar way, here to here also you will get the same. Here also you will get the same. So 4 to 5 you are getting a total of 4 meters. Okay. Now for this problem, you have to calculate the inductance in each side. Okay, that means you have to calculate the inductance LA, and also you have to calculate the inductance LB and that of the complete line. So the complete line inductance will be L is equal to LA plus LB. Okay, right. So then what is the expression for determining the inductance in any side? So LA will be equal to 2 into 10 to the power of minus 7 ln dm by dsa. Okay, so here dm will be the same. Okay, so but self GMD will be different for both the conductors, right? So self GMD of side A will be dsa. So while calculating inductance of side B. So this value will be 2 into 10 to the power of minus 7 ln dm by dsb. You have to take. So this value will be in Henrys per meter. So both the values are in Henrys per meter only. Okay. So now what is the value of dm? So this dm will be same in both the sides. Right. So dm here is the mutual GMD between sides A and B. So which is nothing but, so it is the product of all the possible mutual distances you have to consider. Right. So here this is phase A and here this is phase B. So now first consider the subconductor in phase A or side A. So then the mutual distances from side A to side B will be D14, D15. Right. So D14, D15. So this is one set of mutual distances from side A to side B if you consider the subconductor 1. So if you consider the subconductor 2, then mutual distances will be 2, 4 and 2, 5. So D24, D25. So this will be the another set of mutual distances. Now if you take the subconductor 3, so then mutual distances will be D34 and D35 you will get. So this is another set. Whole to the power of 1 by, so total number of conductors in side A, so which is 3 into total number of conductors in side B, which is 2. So that means 1 by 6 you will get. Here you are getting 1 by 6. Okay. Right. So this is the equation for calculating the mutual GMD for this transmission line. Now, what is the distance D14 and D15, D24, D25, D34, D35? So you have to observe those distances from this figure. Okay. So once you see here D14, D24. So D14 is nothing but, so here to here, this distance. Right. Center to center always you have to take. Okay. So this is D14. The value is not given in the figure. So but this distance is given as 2 meters and also this distance is given as 8 meters. Okay. It is making like a right angle triangle. So this is the hypotenuse according to the Pythagoras theorem. So this value will be equal to under square root 8 square plus 2 square. So which is nothing but 64 plus 4 under square root, which will be root 68. Okay. So D14 will be root 68 meters. Similarly, D25 also you will get the same. Okay. So D25 also you will get the same. And at the same time, if you calculate for D24 also the value will be the same, and D35 also the value will be the same. So all the values D14, D25, D25, D35. So all the values will be equal to under square root 68 meters. Okay. And the value of D15 if you observe. So D15 is the distance from here to here. Okay. How you will get this distance? You have to again make one right angle triangle like this. Okay. So now this side is 8. Now from here to here the total will be 6. So this value will be under square root 8 square plus 6 square you will get. So under square root 8 square means 64 plus 32. Okay. So 36, sorry. Okay. So this value will be under square root 100. So which is nothing but 10. Okay. So D15 as well as if you calculate for D34 also, you will get the same. So which will be equal to 10 meters. Okay. So now you got all the values, all the distances here. Okay. So now D14 is, what is the D14 distance? So D14 is this distance, which is root 68. You substitute here. Okay. So here you substitute root 68 multiplied by D15 is 10 multiplied by D24 is again root 68 multiplied by D25 is again root 68 and D34. So this value is 10. 35 will be again root 68 whole to the power of 1 by 6 you will get. Okay. Here you are having 1, 2, 3, 4. Okay. So root 68 whole power 4 multiplied by, so tens will be 2. So 10 square whole to the power of 1 by 6 you can write. Okay. So now here this square and 2 you will get. So you will get 68 square, and 100 square will be 100. Sorry, 10 square will be 100 whole to the power of 1 by 6, and you calculate the value. You are getting that value will be equal to 8.8 meters. Okay, so the mutual distance, so mutual GMD will be, DM value will be equal to 8.8 meters. Okay, so now you have to calculate the self GMD in each side. So that means DSA you have to find out, and also DSB also you have to find out. Right, while calculating the DSA, so self GMD of phase A, you have to consider the conductors in phase A only. Okay, and you have to consider all the possible distances. Okay, so here in phase A, if you consider the first subconductor, all the possible distances will be D11, self distance D11, then D12, D13. This is one set. Okay, if you consider the second subconductor, so all the possible distances will be D21, D22, D23. So if you consider the third one, so then all possible distances will be D31, D32, D33. So while calculating this self GMD, you have to take only the self distances. You should not take D24, so which will become the mutual distance. Okay, so the DSC will be this all the possible distances by considering each subconductors. So you will write, so then whole to the power of 1 by total number of conductors, which is here 3 whole square. Total number of conductors square you have to write. 3 square is nothing but 1 by. So now here you know the distances, all the distances here. So D11, so D11 and D22 and D33. So this self distances value will be equal to R dash, so which will be equal to 0.7788 times R. Okay, and radius of side A, it is given in the problem itself. So that value is 2.5 mm. Okay, so 2.5 mm here. So that means 0.7788 times 2.5 mm you have to take. Okay, now if you calculate this value, so you will get the value in. So if you want to convert into meters, so in place of m you can take 10 power minus 3. So 0.7788 25 into 10 power minus 3 meters you will get. Okay, so this value. Now here all the distances, if you see here, so you will get the same. So instead of calculating each, so if you find this value, if you find this value, you may be getting the same value, or you can directly substitute the values itself. Okay, so here D11, so D11 is this total value. Okay, so 2.5 into 10 power minus 3 into 0.7788. So this value is D11. So then D12 here is 4 into 4. So D13 is 4 plus 4, 8. Okay, so this is for this set. Okay, so again if you write for this set D21, so D21 will be 4. So D22 will be, so this total value 2.5 into 10 power minus 3 into 0.7788. Okay, into D23 will be 4. Okay, so this is the for second set, and for this third set, so D31, so D31 will be 8, and D32 will be 4, and D33 will be 2.5 into 10 power minus 3 into 0.7788. Right, so these all three products will be the DSA. Right, if you observe all the three products, so this 2.5 into 10 power minus 3 into 0.7788 is there in all the terms. So this total value whole cubed you will get. Then 4, how many times it is appearing? So here 1 4, here 1 4, here 1 4, and here 1 4. So total 4 4s are there. So 4 power 4. So then if you observe the 8s, 8 and 8. So 2 8s are there. So here 8 square whole to the power of 1 by 9. So now if you calculate this value with your calculator, so then you will get the value of DSA. So that value will be 0.367 meters. Okay, so now you got the value of DSA and you got the value of DM. Okay, DM is 8.8 meters and DSA is 0.367 meters. Then you can calculate the value of inductance for side A, so which is LA, and the value of LA will be equal to 2 into 10 to the power of minus 7 ln dm by dsa. Okay, so this value is equal to 2 into 10 power minus 7 ln dm value here is 8.8 by dsa is 0.367. Okay, so now if you calculate the value, you will get the value of total inductance in side A, right? So that value will get here, it will be equal to 0.635 millihenries per kilometer, right? Actually, so this value, if you calculate, you will get in henries per meter. So if you want in henries per kilometer, so then you have to multiply this total value with 1000, so that you will get 2 into 10 power minus 4 into ln 8.8 by 0.367. Okay, so if you calculate this value, you will get this amount. So 0.635 millihenries per kilometer. Okay, so you got the value of LA here. So then how you can calculate the LB? So LB will be LB value. So it will be equal to 2 into 10 power minus 7 ln dm by dsb. So here dm value is known. So dsb you need to find out, right? So dsb, how you can find out? So here you have to consider the phase B or side B. Here in side B you are having 2 subconductors, right? So you have to write the all possible distances. dsb is equal to, so if you consider the 4 subconductor, so then D44 self distance and D45. So this is another distance. Okay, and then if you consider the 5, so D55 into D54 whole to the power of 1 by total number of conductors whole square. That means 1 by 2 square you will get. Okay, and the D44 value and D55 value, this value will be equal to R dash, so which is equal to 0.7788 times the R value, RB. Okay, so this is the RB dash. So RB value is here is in the given problem, what is the value given? This is 5 mm. So that means RB here is 5 into 10 power minus 3. So 0.7788 times 5 into 10 power minus 3 meters you will get. Okay, so then D45 and D54, so both will be equal to 4 meters from the figure. Okay, now if you substitute all this in this equation, so then D44 and D55 both are the same, which is this total value whole square. So then D45 and D54 both are same, which is 4 square you will get. Okay, so 5 into 10 power minus 3, 0.7788 times square into 4 square whole to the power of 1 by 2 square you are having, which is 1 by 4. So the DSB you are getting here with 0.125 meters. Okay, so now you got the value of DSB. So then the value of inductance LB is equal to 2 into 10 to the power of minus 7 ln dm by DSB you will get. Okay, so here it is, this value is in henries per meter. If you want in henries per kilometer, you have to multiply this with 1000, so that it will become d into 10 power minus 4 ln dm by dsb whole to this value henries per kilometer you will get. Okay, so now you substitute the values. 2 into 10 power minus 4 ln dm value here is, so from the previous slide it is 8.8 here, so that 8.8 by dsb is 0.125. Okay, so which is in henries per kilometer. So now if you calculate this value, you will get the value in henries per kilometer. That value you are getting here to be 0.85 into 10 power minus 3 you are getting. So this value 0.85 into 10 power minus 3 Henry per kilometer you will get. So on this 10 power minus 3 you can call it as milli. So the value will be 0.85 into 10 millihenries per kilometer. Okay, now you got the value of LA, you got the value of LB. So inductance of side A and inductance of side B. So the total inductance is sum of the two inductances. So 0.635 plus 1.85. So the total inductance you are getting it to be 1.485 millihenries per kilometer. Okay, so this is how you can determine the inductance of a single phase transmission line if the each phase is having different number of conductors and the radius also different. Okay, right. Let us see this problem. You can work on this problem. So determine the inductance of single phase transmission line consisting of 3 conductors which are having 2 centimeter radii in the go conductor in the sense forward conductor. Okay, and 2 conductors of 4 centimeter radii in the return conductor. So return conductor in the sense it is return path. Okay, so here one side you are having 3 conductors, other side you are having 2 conductors. Okay, so this problem is similar to the previous problem 3. So you can determine the inductance for this transmission line system in the similar way as the previous problem. So but the only difference here is that, so the conductors in the phase B, if you observe, so these are not symmetrically placed. Okay, so here if you see, the conductors are symmetrically placed here. So but here they are placed horizontally to A and B phases. So the conductors in phase Y, so they are calling here X and Y phases. So in phase Y, 2 conductors will be in parallel with first 2 conductors in the same line with first 2 conductors on the phase X. Okay, right here. So you find the distances here T A dash. If you observe, so D A dash is 6 meters from the figure itself. Okay, D A B dash, so is this distance, right? So this distance is not given, but this distance is given, which is 4 meters. So this is 6 meters. So this value will be underscore it 4 square plus 6 square, which is nothing but 4 square is 16, 6 square means 36. So that value will be underscore it 52. So if you calculate this value, you are getting 7.211 meters DAB dash. Okay, so then DBA dash, so AB dash and BA dash, so BA dash, sorry, this distance, so BA dash distances, so this AB dash and BA dash, so if you calculate both the distance, you will get the same, so which is 7.211 meter again. And if you calculate the distance from B to B dash, so B to B dash here is this distance, which is again 6 meters only. So then if you calculate the distance C to A dash is this distance. Okay, so C to A dash is from center to center, you have to take always the distance. Okay, so now you consider it this rectangle triangle. So this value is 6 and this total value is 8. So 4 plus 4, 8. So this value will be 8 square plus 6 square. If you calculate this value, you will get 10. So DCA dash, you are getting 10 meters. Okay, so then if you calculate the DCB dash, so then this DCB dash will be same as DBA dash, which is again 7.211 meters. Okay, so now the inductance of X and Y phases will be LX and LY, and total inductance will be LX plus LY here. Okay, so now how you can determine this LX value? So LX and LY are the per phase inductances. So that value will be equal to 2 into 10 power minus 7 ln dm by ds. So this value is for each phase, inductance value per phase per meter, only for 1 meter. So that means this value is henries per 1 meter. So if you want to calculate for kilometer, so then this value you have to multiply with 1000. So that you will get 2 into 10 power minus 4 into ln dm by ds. The value is in kilometer, henries per kilometer. Okay, so if you convert this into logarithmic term, so that here you are having ln term, which is to the base e. If you convert into logarithmic term, so you will get base 10, right? So then you have to remember this equation. So but generally, instead of remembering this equation, you always remember this equation, which is a very easy equation. Okay, so from this equation only you can solve the inductance in each side of the transmission line. At the same time, total inductance of the transmission line. Okay. So now the mutual GMD of this single phase transmission line is nothing but it is the all possible mutual distances product whole to the power of 1 by m into n. So m is nothing but total number of conductors in X, which is 3. So n here is nothing but total number of conductors in Y, so which is 2. Okay. So now here this is phase A and this is phase B, or this is phase X and phase Y. So now mutual distances in the sense, so if you consider subconductor A, the possible mutual distances will be A dash, A B dash. This is one set. A dash, A B dash. So if you take the second conductor, mutual distances are B A dash, B B dash. So B A dash, B B dash, another set. So then mutual if you consider the C A dash, C A B dash. Sorry, C B dash. C A dash, C B dash is another set. Right? So the product of all the possible mutual distances from each conductor inside A to each conductor inside B, you have to take whole to the power of 1 by mn. So m here is total number of conductors in phase X and n is total number of conductors in phase Y. So this will be m will be 3, n will be 2. So the total value is 6. Okay, 1 by 6 you will get. Okay, and the distances you already calculated here. So you substitute all the distances here, so that the value of dm you are getting here is 7.162 meters. Okay, 7.162 meters you are getting. So then you have to find out the self GMD of side X and self GMD of side Y. Okay, so how you can calculate? Self GMD of side X is represented with dxx and self GMD of Y you can represent it with dsy. So while calculating the self GMD, you have to consider only the subconductors in that particular side only. Okay, so while calculating the self GMD of side X, you have to consider only the subconductors ABC. While calculating the self GMD of conductor Y, so then you have to consider only subconductors of that particular phase only. Okay, then you have to take all the possible mutual distances. So not mutual distances, self distances, right? So here, if you take the phase A, so you are calculating the dsx. So while calculating dxx, you have to consider ABC subconductors. Now, if you consider the first subconductor A, so what are the all possible distances of all these three conductors? So along with the self distance also. So self distance is nothing but DAA, right? So if you take A, DAA, then DAB, then DAC. So that is one set. DAA, DAB, DAC. So now if you take second conductor B, so then all possible self distances will be DBA, DBB, DBC. If you take the conductor C, DCA, DCB, DCC, you will get. So all the possible product self distances you got whole to the power of 1 by n square. So 1 by n square here is nothing but n value is total number of conductors in that particular phase. So here in phase X you are having 3 conductors, so it will be 3 square. Okay, so in place of m you have to take 3 square you will get. So 3 square will be 9. Okay, and the values of all the distances here in this equation you already know. Okay, so DA, but here DAA self distances, DAA, DBB and DCC, this value will be equal to RX. RX in the sense radius of each subconductor in phase X, RX dash you have to consider. So that value will be equal to 0.7788 times Rx. Okay, Rx is the radius of conductor in side A. So that means this value is 2 centimeters. So here the value of Rx is 2 centimeters. So if you substitute 0.7788 times Rx is 2 centimeters. Okay, so if you want to convert this value into meters, you have to divide this with 100 so that this value will be in meters. So Rx dash, so this value will be equal to 0.7788 into 2 by 100 meters. So that value are getting 0.015576 meters. Okay. So now the other distances, AB, AC, BA, BC, CA, CB, all distances you know from the figure itself. So you substitute all the distances here in this equation. You will get the dSx. That value you are getting here to be 0.734 meters. Okay. So the Lx value. So Lx value, how you can determine? So that Lx value is equal to 2 into 10 power minus 4 ln dm by dsx. So which is in henries per kilometer. Right. So this is power 4. So if you substitute dm value here and dx value here. So what is dm? So dm you are getting this value 7.162 and dsx you are getting 0.734. If you substitute those two values here in this equation, you will get the value of Lx, and the value of Lx is 0.455 millihenries per kilometer you are getting. Okay. So in a similar way, you can calculate the inductance of side B also. So here in side B or side side Y, here you are having two subconductors. Only two subconductors, A dash and B dash. So you have to write all possible self distances d A dash into d A dash B dash. One set. Another set is d B dash d B dash A dash whole to the power of 1 by total number of conductors square. So that means 2 square. So which is 1 by 4 you will get. Okay. So and this A dash and B dash value. So these two values are same, which will be equal to Rx dash. And this Rx dash will be equal to 0.7788 times the Rx. Sorry, Ry here. So this is Ry. Ry here in the for problem it is given as 4 centimeters. Right. If you want to convert that into meters, you have to divide with the 100. So 0.7788 by 100 into that 4. So which you will get in meters. So Ry dash which will be equal to d A dash or d B dash. So that value you are getting it to be 0.031152 meters. Right. So now if you substitute all the values here in this equation, so then you will get the dsy, and the dsy is 0.353 meters you are getting. Okay. So then the inductance of side Y, so which is Ly will be equal to the same equation 2 into 10 power minus 4 ln dm by dsy here. Right. Dm value will be the same, which is this value 7.162 meters, and dsy is 0.353. So then if you substitute those two values here in this equation, you will get the value of Ly. So that value is you are getting it to be 0.602 millihenries per kilometer. Okay. So now the total inductance will be sum of the two inductances Lx and Ly. So then if you sum those two, you are getting the total inductance of that particular transmission line will be equal to 1.057 millihenries per kilometer. Okay. So like this, you can calculate the inductance of a transmission line. So for any configuration, if each side is having the same number of conductors and same radius, you can determine. And if the conductors, if each side in the transmission line you are having different number of subconductors, one side 3 subconductors, other side 3 subconductors or 2 subconductors, you can determine the inductance in the similar way. Okay. Okay. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.